and the other is left-handed. They are made of the same stuff, but they are arranged just a little bit differently. Well, molecules can be like that too. Some molecules are like chemical twins, wearing the same outfit of atoms but standing in a completely different pose. This amazing chemical trick is called isomerism, and it is happening all around us, and even inside of us right now. It's a fundamental idea in chemistry, and once you see it, you'll start noticing it everywhere. Science is cool like that. So, let's break it down. The word isomer comes from Greek words, isos meaning equal, meros meaning part. So, isomers are molecules that have the exact same number and type of atoms, but those atoms are arranged differently. Alright, let's dive into our first big family, the structural isomers. These guys are the master architects of the molecular world. For structural isomers, the rule is simple. Same atoms, different connections. The very blueprint of how the atoms are bonded together is what changes. You have all the same people on the list, but who holds hands with whom can create a completely different chain of people. We can even break this family down into a few smaller groups based on how the blueprint changes. It's all about the order of assembly. First up, we have chain isomers. This is probably the simplest type to picture. It's all about how the main carbon backbone, or chain, is put together. You could have one long, straight string of 4 bulbs. Or, you could take that same string and have 3 bulbs in a row with one branching off the middle. You still have 4 bulbs, but the shape of the string is different. A great chemical example is butane, which has the chemical formula C4H10. In one form, N-butane, the 4 carbon atoms are linked in a straight, unbranched line. But in its isomer, isobutane, 3 carbons form a chain, and the 4th one branches off the center carbon, like a T-shape. Next, let's meet the position isomers. With these molecules, the main carbon skeleton stays the same, but a specific atom or group of atoms moves to a different spot on that skeleton. The room's shape is fixed, but you can move the lamp from one corner to another. Consider the molecule propanol, C3H8O. In one propanol, the special OH group, which makes it an alcohol, is attached to a carbon at the end of the 3-carbon chain. But in its isomer, 2-propanol, that same OH group has moved to the middle carbon. Same backbone, same special group, just a different address. Finally, we have the most dramatic of the structural isomers, functional group isomers. These are really cool because even though they have the exact same atoms, they rearrange them to form completely different types of molecules, or what we call different functional groups. This is like taking your Lego bricks and building either a car or a boat. The pieces are identical, but the final object has a totally different function. A classic example is C2H6O. With this formula, you can make ethanol, which is a type of alcohol. But you can also arrange those same atoms to make dimethyl ether. Ethanol is a liquid that mixes with water, while dimethyl ether is a gas. They have completely different chemical personalities. Now, let's venture into a different dimension of isomerism. If structural isomers are about changing the basic blueprint, our next family, the stereoisomers, is about keeping the blueprint the same, but arranging the parts differently in 3-dimensional space. The atoms are connected in the exact same sequence, but their spatial orientation is different. It's chemistry in 3D. Section 4. Same side, opposite side. The geometric cis-trans game. Let's zoom in on our first type of stereoisomer, the geometric isomer. You'll often hear these called cis-trans isomers, and the name gives us a huge clue. In Latin, cis means on the same side. Trans means across or on the opposite side. These isomers pop up when you have a rigid structure in a molecule that prevents free rotation. Most commonly, a carbon-carbon double bond. Think of that double bond as a solid, flat plank between 2 wheels. You can't twist one wheel without twisting the whole plank. This rigidity creates a fixed top and bottom relative to the plank. Let's use a great simple example, a molecule called 2-butene, C4H8. In the middle of this molecule is a carbon-carbon double bond. Each of those two carbons is also attached to a hydrogen atom and a methyl group, a small CH3 group. Now here's where the fun begins. We can have both methyl groups on the same side of that double bond plank. When they are together on one side, we call it cis-2-butene. It's like two friends sitting on the same side of a canoe. But what if they're on opposite sides? You guessed it. We can also have a version where one methyl group is on one side of the double bond, and the other methyl group is on the opposite side. This arrangement is called trans-2-butene. It's like our two friends are now sitting on opposite sides of the canoe, balancing each other out. The atoms are all connected in the same order: carbon, 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 carbon. But their spatial layout is different. You can't just twist the trans version to make it the cis version without breaking that rigid double bond, which would take a lot of energy. Cis-2-butene and trans-2-butene are real, distinct molecules with different properties. Section 5. The mirror trick, meeting the optical isomers. Now for our second, and perhaps most mind-bending, type of stereoisomer, optical isomers. These are also known as enantiomers, and they are true molecular mirror images. Remember our hand analogy? Your left hand and your right hand are perfect mirror images, but they are non-superimposable. That's a fancy way of saying you can't place one perfectly on top of the other so that all the parts line up. This property of handedness in molecules is called chirality. The most common cause of chirality in organic chemistry is a carbon atom that is bonded to 4 different groups. We call this a chiral center. Think of that carbon as the wrist, and the 4 different groups as a thumb, a pinky finger, a ring, and a watch. If you build a mirror image of that wrist, you get the other hand. You simply cannot rotate one to become the other. They are forever locked as left and right-handed versions. A wonderful example from our own bodies is a molecule called lactic acid. When you exercise really hard and your muscles feel that burn, it's because they are producing lactic acid. Lactic acid has a central carbon atom bonded to 4 different things, making it chiral. This means there is a right-handed lactic acid and a left-handed lactic acid. They look identical in the mirror, but they behave differently in biological systems. The right-handed version of carvone smells like spearmint, while its left-handed mirror image smells like caraway seeds, the scent in rye bread. Section 6. Why it all matters, from flavors to pharmacy. We've journeyed through the world of isomers, the structural architects, and the 3D stereoisomers. We've seen how molecules with the exact same formula can be as different as a straight line and a T-shape, or as subtle as a left hand and a right hand. Well, it matters immensely. Isomerism isn't just a quirky chemical fact. It is a principle that governs everything from the flavor of your food to the effectiveness of your medicine. Since our bodies are built from chiral molecules, often only one enantiomer of a drug will fit correctly and produce the desired effect. Understanding and separating isomers is a huge part of creating safer and more effective medicines. Fun fact, the molecule limonene has 2 optical isomers. One smells like oranges, and its mirror image smells like lemons. Same atoms, different shape, different world.